Okay, so it looks like we're on time. Hello, everyone. Welcome to our MIT Cyber Series seminar. So today we are very delighted to invite Professor Yang Xiang from the Swinburne University of Technology. He will introduce his research on the topic of software vulnerability detection by fuzzing and deep learning. So before we start, I would like to do the acknowledgement of country. So we acknowledge that the people of the Wurrung and the Boonwurrung language groups of the East Koolie Nation, whose unceded lands we conduct the business of MIT University, and the lands that I'm speaking from today. We respectfully acknowledge the First Nations people of the First Koolie Nations, their ancestors and elders past, present, and emerging. MIT also acknowledges the tradition custodians and their ancestors of the lands and waters across Australia where we conduct our business. So afterwards, I'd like to take some minutes to introduce our MIT Center for Cybersecurity Research and Innovation. The MIT University Center for Cybersecurity Research and Innovation, also known as the CCSRI, is a multidisciplinary research center that brings researchers from across MIT to bring a truly multidisciplinary approach to the organizational, human, and technology aspects of cybersecurity. So afterwards, let's celebrate some achievement of our center's member, Nasrin Sorabi, who has authored her first textbook titled Data Filtration, Threats, and Prevention Techniques. Published by Wiley, this book delves deep into the realm of cybersecurity with a particular focus on malware detection. So congratulations, Nasrin. Well, the final thing about our center is that we have the HDR Cyber Club. So everyone, you're welcome to join the center's HDR Club. So feel free to email this address, ccsri@mit.edu.au, to send the Teams message to Amy Hall to join the club. So, okay. Let's start our introduction to today's invited speaker, so Professor Yang Xiang. So Professor Yang Xiang received his PhD in computer science from Deakin University, Australia. He is currently a full professor and dean of digital research, Swinburne University of Technology, Australia. His research interests include cybersecurity, which covers network and system security, data analytics, distributed systems, and networking. In the past 20 years, he has been working in the broad area of cybersecurity, which covers network and system security, AI, data analytics, and networking related cybersecurity. He has published more than 300 research papers in many international journals and top conferences. He is the editor-in-chief of the SpringerBriefs on cybersecurity systems and networks. He serves as the associate editor of the ACM Computing Surveys. He also served as the associate editor of IEEE Transaction on Dependable and Secure Computing, IEEE International Internet of Things Journal, IEEE Transactions on Computers, and IEEE Transactions on Parallel and Distributed Systems. He is the coordinator, Asia for IEEE Computer Society Technical Committee on Distributed Processing. So he's a fellow of the IEEE. So welcome, Professor Yang Xiang. And so I'm going to stop sharing my slides, and then the floor is yours.
Thank you very much, Maggie. And thanks everyone for coming to this seminar. This is a great opportunity for me to share some research from my team. Let me just share my screen. Okay, can you see my screen okay?
Yeah, we can see your slides.
Perfect. Perfect. Okay. We've been just talking about the cold weather in Melbourne, but thanks again for all your warm welcome to join this seminar, and hopefully we can utilize this opportunity to discuss research and possibly to discuss some collaboration. So before I start, Maggie just mentioned that I'm working on the Springer book series about cybersecurity. So if you want to publish anything in this book series, please feel free to let me know. I can work with you on the book proposals. So the book proposal doesn't have to be very long. So this is a Springer format, and it does have some page limits. So if you have any good work, please feel free to let me know. Okay, so today my topic is about software vulnerability detection. And I hope to give you some broad view about this research area and the challenges and research gaps and possible solutions. And my group have been working on this research field for a few years by utilizing a few approaches. So it could be deep learning, could be fuzzing, it could be a mixing of different approaches. So I'm very pleased to have this opportunity to share with you our experience and the lessons learned. All right. Before I start the technical part, I also want to acknowledge the wandering people of the Kulin Nation, who are the traditional owners of the land, which Swinburne University's Australian campuses are located. And I would like to pay our respect to their elders past, present, and emerging. So here is the outline of this talk. So first, I want to give you some brief overview of the software vulnerability detection problem. And then we move on to two scenarios. So, you know, when you are dealing with this, a piece of software, often you got two scenarios. One is that you got the source code, and the other is that you don't have the source code, but you do have the binaries. So I want to categorize the problems into these two streams, and then we talk about what are the challenges in these two different scenarios, and then we come out some solutions, challenges, and future directions. Okay, so I guess that's pretty straightforward, right? So I also hope that we can utilize this as an more discussion-like talk instead of just me talking about what the problems and the solutions. All right. So if you have any questions, just let me know, and we can discuss the questions. Because I'm presenting this on my laptop, so if you post any questions in the chat box, then I might not see your text in time. So please feel free to just yell out if you've got any questions. All right. So first of all, let's talk about the problem. So why this problem is so important? Because nowadays, almost everything is driven by software. So we have been talking about data analytics, big data, machine learning, AI, automation, robotics. But when you are looking at different systems, everything is actually driven by software. So that's why we are so keen to look at the software vulnerability problems because the applications are so wide. We have seen software vulnerabilities as the main cause of different types of cyber attacks. So I don't have to mention how much money have been lost during these different types of cyber attacks. But the key or the root cause is often software vulnerabilities. So software vulnerabilities are something that is hidden in the software, and it is often ignored by the developers and often picked up by the cyber attackers. So this is a very brief history of the most recent vulnerabilities, such as in 2014, Heartbleak and Shell Shock affected millions of web servers. And then in 2017, the Crypto Locker, which is essentially a malicious software that is to lock all the computers. This is actually a kind of attack which is caused by some software vulnerabilities on Windows. In that attacks, almost 4 billion has been lost, and there are millions of computers from more than 150 countries were affected. And also in 17, 18, there are different types of vulnerabilities such as Spectre, Meltdown, and Intel SGX vulnerabilities. So the incidents are very, very significant. If you look at the Spectre and Meltdown vulnerabilities in the firmware, then the significance cannot be ignored, because 7 to 8% of the CPU performance were lost. So which means the CPU performance is often improved every year by 7 to 8%. So which means at that time, if we want to fix the vulnerabilities, we have to lose the CPU performance for the whole year. So this is significant. Let's talk about the challenges. So we know software vulnerabilities are a huge problem, but why it is so difficult to deal with? So first of all, the number one challenge is about the software complexity. Nowadays, the complexity can be measured by the size of the software, for example, the lines of the source code. So in here, we just listed the current software suite, the lines of their softwares. So nowadays, the operating systems such as Debian and Mac OS could reach 100 millions of lines of source code. So the size means it's very big, right? And also the other measurements is the dependency of different functions, different components of the software. So the dependency is also another measurement of the software complexity. So nowadays, almost every piece of software has been very, very big and very, very complex than ever. So that's the first challenge. The second challenge is about the vulnerability numbers. We have seen there are so many vulnerabilities from different families, like malware, right? So you have seen a lot of new vulnerabilities coming out every day, and this data on this screen is old because we only listed the data up to 2018, but the new vulnerabilities are actually in the trend of fast increasing. So so suppose you got an ideal machine learning algorithms that can pick up every single pattern that can reveal the real vulnerabilities. But if the vulnerability numbers are increasing every day, how this machine can train its model and how it can give a precise prediction, this is a huge problem for all machine learning based algorithms. And the third challenge is about data. We have been talking about data for almost everything, and we know that nowadays we do have the capability to collect and make use of the data. However, in the software vulnerability area, a few properties are always ignored, such as efficiency, effectiveness, and scalability, because when we are looking at the data, we actually lack of the ground truth data, we lack of labeled data, we don't really have enough computing resources to pre-process the data for a better machine learning training, and we don't really have that good human resources to actually examine the data, and also there are also as a human, we also lack of security related knowledge to process the data. So although we know that we have the capability to collect the data, we don't really have the good data. So that's why we thought that the lack of data is one of the significant challenges. Okay, so if you got the source code, then we will deal with the source code as something that the machine can process. So that's the good thing if you got the source code. Although we have just talked about the number one challenge is the software complexity. We have to process a huge amount of source code. All right, so in software analysis area, there are a few categories of methods, such as static methods, dynamic method, and hybrid method, which is to combine static and dynamic method. So when we are looking at the static level of analysis, we categorize them into unit level, technology level, and system level. So there are different tiers of analysis approaches. But when we are looking at the source code as a static information, then the static approach is a pretty powerful tool that can deal with the source code. So nowadays, there are many tools that can understand the source code by converting the source code into some patterns that machine can understand. So eventually, we will utilize this approach to convert source code into effective features. So the good features are representative features, invariance, and distinctive. So which means that we can differentiate one piece of code from another piece of code automatically and by using pattern recognition. So the key issue here is how we can understand the code. So code semantics is the key issue. Often detection systems are incapable of fully understand the code semantics as human do. It's because when human are checking the source code, we often understand some tiny issues according to our previous experiences, such as some memory handling issues or some loop issues. So when we are looking at this, we want to make the machine to mimic the human behaviors and trying to train the machine as good as human. Then the machine can understand the software vulnerabilities into some numeric features that can be processed automatically. So that's the issue. So the research gap here is that the semantic gap. So how to let the machine run as fast as the human or as clever as the human, however, to utilize the machine power to accelerate this process. So the semantic gap means the gap between a knowledgeable and experienced practitioner and the machine-based detection systems. So we need to bridge that gap in order to make a software detection algorithms more powerful. So then we thought about different existing algorithms. So when we are looking at the software vulnerability detection issues, we often look at different types of existing algorithms. So one of the area that we recently look at is the representation learning. So there are a few algorithms which we can utilize, and we need to find out the best algorithms that can represent one piece of software into something that can best represented by the training models. So we had a look at different structures, and we find a good structure that can capture the structure of the source code, not only the parameters, but also the structures of that piece of source code, which is, we call it as AST, abstract synthetic tree structure. And then we convert that into some data structure that can be processed automatically by the machine learning algorithms. And we also look at this problem as a very high dimension nonlinear problem. Because deep neural networks have been used in the most recent years, and they got quite good results in other domains problems. And then we look at if we can actually use deep learning algorithms. So we found out that it's actually quite good in understanding the underlying rich semantics of the source code, because we look at the source codes as the language data. So it can be used to fit nonlinear and abstract patterns and capture some meaningful words. Why we look at the source code as a language problem, because in the language there are a lot of semantics in the software. For example, if we are looking at some memory handling process, so first of all, you define a piece of a memory allocation by using some parameters, and then after that, there are often some memory handling processes, such as a memory copy or memory remove or something like that. So there's always this kind of semantics similar to natural language. So that's why we look at the source code as a language problem. So there are a few ways to represent that kind of a structure, such as the graph-based, the sequence-based, and text-based, and the mixed-based structures. So one of the project we want to share with you is the cross-project transfer representation learning for vulnerable function discovery. So in this project, our goal is to find out the vulnerable functions in source codes. So this work is a function level. So which means we can find out the vulnerable functions. However, you need to find out where it is exactly within that function by human. So the automation is at the function level. So in this work, we find out that the problem is that we often find that some projects vulnerability, which contains the vulnerabilities, often happen in different other projects because multiple projects share some vulnerability functions. So which means we utilize the representation learning to transfer the knowledge learned from one project and then to the other project. And then we utilize the classifier to find the potential vulnerability functions. And there are a lot of details on how we can handle the knowledge transfer, how we can handle the classification by using different types of classifiers, and how we can rank the outputs into a list and give some reasonably reliable outcome of the labeled vulnerabilities. And then we expand that work into multi-domain knowledge and use a multi-domain knowledge bases. So this is the work expand that part into multiple learning machines and then give the some more reliable and precise results. So and then we carried out some research works based on both cross-domain knowledge transfer and also the deep domain adaptation algorithms. So we expand that into even more complex scenarios. And also because the existing machine learning algorithms are often based on historical data. And it's very hard for machine learning to give a precise prediction for new vulnerabilities. So that's why we introduce the fuzzing algorithms. In a few minutes, I will give you some brief background of the how fuzzing works. The beauty of fuzzing is that it can be used to detect new vulnerabilities. So we combine deep learning and fuzzing into a whole framework. and to give a more precise prediction for both old and new vulnerabilities. So essentially, if you got source code, you're lucky because you have something to process. However, there are a few challenges in this particular approach. First of all, we often, when we are talking about the grand challenges of software vulnerability detection, we often talk about that we don't really have the data. So it is important to get the ground truth data set and to get a reliable data set that can summarize the real semantic meanings of the software. So there are some public available data sets for testing. However, in general, we don't really have enough ground truth data sets. Our research lab also produced some data sets, and we open source the data sets on GitHub. So if you want to utilize any data set from our group, please feel free to let us know. The second challenge is a lack of model interpretability. Nowadays, we want to know some reasons behind the learning machines, and we want to know if the output is trustworthy. So we need to find out the reason. So at this stage, this is a new area, and there are many researchers are working on that. The third challenge is a neural model with a semantic reservation. When we are translating something from the source code into some models, we often lose information. So we want to preserve as much as the information possible. And also we want to make sure that representation is reasonable and feasible. And the last challenge is about code representation learning. So it involves cross-domain transfer, and we also need to develop more powerful engineering technologies to make sure that the source code can be converted into some meaningful things. Okay. So I think that's pretty much about the scenario if you got the source code. Now we move on to more complex scenarios. That is, we don't have the source code. We only have got binaries. This is a very common. If you buy some software for a large-scale commercial use, often you deploy the software in your organization, and you don't know if that piece of software is trustworthy, and often because it is deployed in the very complex environment, it's very hard to find out if the binary can do anything wrong within your organization, and often you don't have the source code, and the software vendors often don't provide the source code. So there are two streams of the binary level software vulnerability analysis. So traditional ways, there are a few ways, such as fuzzing, symbolic execution, taint analysis, or some combination of different analysis approaches. We call them as traditional techniques because they have been there for decades since the development of the software. However, they are very powerful still. They are very effective. So nowadays, fuzzing is still one of the mainstream techniques that is used to deal with the binary level software vulnerability problems. And the new algorithms could be used based on machine learning techniques. So again, you got dynamic analysis and static analysis by using different learning frameworks, such as supervised learning framework and unsupervised learning frameworks, or the hybrid of different learning algorithms. But when we are using machine learning algorithms, it faces significant challenges because we are dealing with the binaries. So this is the area that requires the knowledge from software engineering and cybersecurity. So the deep learning based algorithms requires the knowledge of the machine learning algorithms, and also the how we can handle the software in the form of binaries. If we look at the one of the streams, which is based on machine learning, then the focus is on how we can convert the binary into some reliable machine learning models. So the focus is on how we can translate one thing into another. So again, the challenge is similar to when you have the source code. So but even harder, because we need to use the reverse engineering to convert the binaries into some mid-layer language, then convert the language into some meaningful works by using different ways. Say, for example, to select a good feature and then move on to the classifiers. So we actually in this world we develop some software which we call it as a BIVD, which means automatic vulnerability detection based on the binaries in our previous projects. So we have developed some algorithms that can process the Linux-based binaries and Windows-based binaries into some instruction-level code, and then convert that into something the machine learning can process. So we developed this software, and this is the demo interface. So the users can upload their binaries into this system, which is a web-based interface, and then the machine can process the binaries. As I said, this is based on Linux and Windows. So now we can process these two types of binaries, and then in the back end, it has the trained model, and it uses the deep learning based algorithms to process the function level vulnerabilities, and then it gives a ranking of different functions. So for example, here we got 209 functions in this binaries, and then we give the indication of the vulnerable issues in 2 functions, and then we give some warnings if the possibility is not that high. Okay, so that's one stream that we can use if you got a binaries and you got a very powerful machine learning algorithms, and now let me use a few minutes talking about the other stream, which is fuzzing, which is to use fuzzing to find out some new vulnerabilities. So fuzzing is actually, the concept is very simple. So we feed the software with some inputs, and then we look at the outputs of the software. So if the outputs are abnormal, then that means something is wrong in this piece of software. So that is a random process and a repeated process to test the piece of software. This is often used to test the software bugs previously, and nowadays this is one of the most powerful approaches to find out the vulnerabilities. So there are a few questions to ask when you are using fuzzing. So first is how to formulate the fuzzing processes more precisely, and what is the limitation of the fuzzing. No matter how powerful your fuzzing box is, there are many limitations of this approach, and how to purposely design the outputs or effective feedbacks. So we can design the input, and also we can design the output to make sure you got the very powerful output. So as we know, this is pretty much a random process. So if we say, for example, if you use brute force to crack a password problem, then the search space is huge. So this is similar in the fuzzing process. So how we can reduce the search space more effectively is one of the key issues, because in this way we can significantly reduce the search time, and how we can infer the format of input and output. So in some systems, so for example, the communication systems, you can't really control the output format, because you input one bit, you got 3 bits or 100 bits as outputs, so you can't really control the format. And also how you can design the effective mutation operators, and how we can make a good automation of execution of the fuzzing, because we want the fuzzing machines to run by itself, and eventually we hope the fuzzing machine can give reasonably short outcomes. If it is not too long, we don't really have the human power to read the long list of the vulnerabilities, so which might contain a huge number of false positives. So that's the philosophy of making an effective fuzzing algorithms. So guided by this philosophy, we develop a work which is called a defuzz work, because we find out that deep learning algorithms can automate some processes of the directed fuzzing algorithm, because we can automate that process, and to make the output containing less false positives. So this is probably one of the first work in the world combining the deep learning algorithms and fuzzing algorithms. And we found out it has pretty good outcomes, and by reducing the false positives. So we tested the algorithms by different data set, and and of course, the different types of data sets are publicly available. And we found that our algorithms does have the capability to find out new vulnerabilities if we compare it to the previous work. Okay, I guess that's pretty much I want to cover because fuzzing is actually some new area combining with the deep learning algorithms. This is still a new area, although fuzzing have been significantly used by different research groups to find out new software vulnerabilities based on binaries. This is combining both algorithms is actually pretty new, and we hope to achieve a few things. So first of all is to reduce the false positives, and second is to find out the new vulnerabilities, and the third is to improve the detection accuracy. So these are the different areas we want to touch on. And eventually, we want to build an automated framework that can give the end users some confidence that my piece of my software is reliable and trustworthy. So so there are different types of users. So the end users can be someone who use the software and who want to make sure their organization is use a trustworthy software, and also the developers or the designers. We also want to give the designers some help when they are developing their software, if they can actually build reliable software which contains as less as possible vulnerabilities in their source code. So in summary, we got some research work in two streams. One is that you got the source code, and the other is you don't have the source code but got the binaries. So we have published a number of work in different venues, such as the CCS conference and ACM Computing Surveys and different types of journals. So I only listed some review work in different areas with the different focuses, such as fuzzing or deep learning based or data-driven based, or by using deep neural networks to find out software vulnerabilities, or Android platform vulnerabilities. So I think that's pretty much I want to talk for this topic. Please feel free to ask me any questions. Thank you.
Hey, Professor Yang, thank you for coming to give this great talk. It's really impressive. I'm not sure whether this research is funded by ARC already.
We did have an ARC discovery project supporting one of the areas. And we also got some funding from the Next Generation Technology Fund to run the binary-focused vulnerability detection. And we, of course, we publish the papers based on different projects.
Okay, that's great. I know for the software vulnerability detection, there's one area actually focus on like a security software, for example, authentication. Or have you done any kind of particular research on like a security software vulnerability detection?
Our work is probably more generic instead of looking at specific types of software. At this stage, we had some pilot work in the application layer. So, for example, we had some pilot work on finding out the drone system software vulnerabilities and the car control system. So our direction is more moving to the control system vulnerabilities, but definitely this is a good area we would like to explore because the work that we have developed are more generic, and we hope that we can apply our algorithms to different areas.
Okay, that'd be great. My last question is that have you commercialized the software as the products already?
No, that's a very good question. We haven't got any commercialization work yet, although we file a patent on one of the algorithms, but we haven't actually commercialized anything yet. If you got any suggestions or any link, please feel free to let me know. I'm more than keen to work with all of you to commercialize this technology.
Sure. I think that is a great idea, and we are got a lot of application or impact. That's definitely should consider. But it's good to hear you got the patent about one of your research results. Congratulations. Yes, thank you. That's all my questions.
Thank you, Professor Yang. Very interesting and practical talk. And do we have any other questions from our audience? Ibrahim,
yeah,
please.
I would like to ask a question. How are you?
Good, thanks. How are you, Ibrahim?
Not too bad. My first question, the smart contract issues like Solidity and other things. So how suitable your tools are, your methods are to detect problems in smart contracts like Solidity, for example?
That's a very, very good question. We actually to answer your question, I actually got some idea about Xing's question about the commercialization. I said no, we haven't commercialized the core technology, but actually I was wrong. Actually, one of our PhD students applied the technology in looking at the smart contracts. And because that PhD students have already graduated, and they actually got their business on smart contract auditing. So they use similar algorithms that can actually find out some logic vulnerabilities on smart contracts. So in summary, to answer your question is that this is actually applicable in finding vulnerabilities in smart contracts. Yes, it's working.
Okay, thanks. I think, there are issues like re-entrancy attack or DAO attack in the smart contracts. So one of our students was looking into it at some point, of course, not any longer, but at some point. So that's why I was thinking like how your method could be suitable. My other question would be like, this I'm involved in an European project, and these car companies in Germany, they are looking for some static binary code analysis. And I see that you're doing something like that. So I have no clue about these things, how to detect issues in firmware with static analysis. So again, how could we, do something perhaps together? I don't know, because I know nothing about this. So is it possible really to detect, like, provide a binary like the firmware, and your tool can detect some issues there, abnormality at least?
Yes. Because the fuzzing is actually a generic approach. It can deal with the software, the binaries, or when one of our work, which is called black box fuzzing for IoT firmware, which was published in the CCS conference. So that work is exactly looking at the firmware vulnerabilities by capturing the input and the output of the communication channel. So this is not a 100% software vulnerability, because it's captured the communications between different systems. So we did find out that is feasible to find out the firmware vulnerabilities. So I guess that is very important for the car companies to test their firmwares, because we had a look at the systems on normal cars. Normally, in one car there are 5 different systems. So they are linked, or they are kind of separate, 5 types of control systems. And we don't have the source code for each component. So this is actually a quite effective way to find out the vulnerabilities on firmware. So Ibrahim, if you got any thoughts on how we can work with any European car manufacturers,
I will get back to you.
I will to work with you.
Yeah, I think that would be fantastic. Thank you very much. I will give you a call and we discuss. It's I think the university which is involved with this European project.
That would be great.
Yeah. I mean, I when they told me, I felt like, oh, how is it even possible? You look at the firmware, you find out something magically. How is it possible? But it looks like something is doable. Okay, thank you. I will give you a call.
Yeah, thank you.
Okay, thanks.
Thank you, Professor Yang. I think we can have one last question. So from Andy. So would you mind to unmute yourself and ask your question?
Yeah, hello. Thank you.
Hi, Andy.
Yeah, for the great talk. Actually, just a very quick question regarding, I'm very interested in the binary detection. So one is how would you deal with the software update? So when the software be recompiled, then your binary will change, right? Do you still keep the same, or can utilize the previous detection? So that's why, and also based on that, how fast you can actually go through, let's say, a quite a big binary, because sometimes the binary are very large.
Yeah, correct. That's a good question, Andy. So if you patch the system, we have to run the test again. So because the almost everything when you have run on the previous system has changed. So you have to rerun the fuzzing test. In terms of the performance, currently that's also a bottleneck problem. We often run a fuzzing test for 24 hours. And this is not super fast, but in many scenarios, it's still regarded as a feasible approach because you on the next day you got a result.
Yeah. Okay. Fantastic.
Yeah.
Yeah. Thanks.
Can I have a very quick question? So thanks a lot, Professor Yang, for the great talk. My question is about the smart contract. So I'm quite interested in asking about whether there's any available kind of software. You mentioned that your student actually kind of commercialize it to the certain level. So is there like available online software or anything available to test the smart contract?
Yes, there are a few companies got their system, but they are not for free. So they charge quite a high rate to for smart contract auditing. The one of the company is called Chain Analysis, and probably you know that. And the other is I can't remember the other company's name, but there are a few tools that can be used for smart contract vulnerability detection. They are commercial software, and I don't know if there's any free software that we can use.
No, I'm just interested in your students' work. Rather than other company, or is it like still under development?
They have already got the product. I can link you with the my students' company, and then probably you can try if their product can help you to find out your software vulnerability.
I can follow up with you. Yeah, thank you very much,
Yeah,
Professor.
sure. Please feel free to send me an email.
Thanks, Professor Yang, for your great talk. This is very inspiring, and I'm so glad that we had a very good discussion. So due to the time limitation, I think host question will be the last one. And yeah, thank you again. Thank you everyone coming to our center seminar, and thanks again, Professor Yang, for your great talk.
Thank you very much. Thank you. Bye-bye.
See you,
Thank you very
everyone.
much.